Okay, so in this video, I want to discuss a series or the beginning of a series of lectures on protein structure, starting with the simplest, which is primary structure. And you can think of primary structure as being the linear sequence of amino acids in a peptide. And that linear sequence is going to be held together and stabilized by covalent bonds. Specifically, the covalent bond of interest is an amide bond. And those amide bonds in this course we will refer to as peptide bonds. So I'm going to first sketch a generic tripeptide below with correct formal charges at pH 7, and then we will examine where the peptide bonds occur. So when you see a peptide, it's generally written from N to C terminal. So that here you have a positively charged ammonium ion. And then on the far right, you have a negatively charged carboxylate ion. In other words, we're going to find that cysteine, this amino acid here, has a free ammonium ion, or its nitrogen primary amine was not involved in forming an amide bond, while alanine at the other end has a free carboxylate. So that's the meaning of N prime and C prime. So if you're going to draw a tripeptide, that means that you need to have 3 carbonyls, 3 nitrogen atoms, and 3 alpha carbons. So the alpha carbon here is alpha to the first carbonyl and the ammonium. At pH 7, the ammoniums will be fully protonated because their pKa is 9. So we are still more acidic than the pKa. And then the nitrogen of lysine has formed an amide bond with the carbonyl of cysteine. And then you just continue with this sequence of nitrogen, alpha carbon, carbonyl. So the carbonyls are going to alternate so that 2 consecutive carbonyls are anti to one another. So now, if you want to ensure that you have the correct stereochemistry at the alpha carbon, you need to install a dash whenever the alpha carbon is a vertex downwards, and a wedge whenever the alpha carbon is a vertex upwards. And that will ensure that these 2 groups are trans to one another. 2 consecutive substituent chains are always 180 degrees or trans about the amide bond. And then simply installing the R groups, where cysteine is a thiol, lysine is a 4-carbon chain followed by a primary ammonium ion, and then alanine is simply a methyl group. So I'll leave this one as is. That's your tripeptide at pH 7. There are pKa's for these. 2 side chains are ionizable. However, the pKa of the thiol, 8.36, is higher than pH 7, so that one remains protonated. The pKa of lysine is 10.5, which is much more basic than pH 7, so it also remains protonated, as does the pKa of the N-terminal here, which is around 10.7. The only one that will be deprotonated is the carboxyl, because that pKa is around 2. And therefore, we are more basic than that pKa and has been deprotonated to 100% in solution. The last part of this is identifying the amide bonds. So I'll highlight those amide or peptide bonds below. The first amide bond is the CN bond connecting the N-terminal of lysine with the C-terminal of cysteine, and the second amide bond is connecting alanine with what was lysine. So if you have a tripeptide, then you have 2 peptide bonds to link those 3 amino acids together. So you always have 1 less peptide bond, or N minus 1 is the number of peptide bonds, where N is some integer value that is the number of amino acid residues. So you want to be able to draw those tri and polypeptides with correct stereochemistry and correct formal charges at a given pH value. Okay, so let's sort of focus in on that peptide bond now and discuss how it has many consequences for protein structure and stability. And all of this stems from the importance of a resonance structure, where we take that nitrogen lone pair and donate it into the carbonyl of the amide and delocalize electron density onto the oxygen. So this is going to produce a charge separated or a zwitterionic resonance structure, where you develop a CN pi bond, and there's a positive charge on nitrogen since it donated electrons, and now a third lone pair appears at the carbonyl oxygen. There were 2 before. And this is a zwitterion. There are formal charges, but the net charge is 0. And it turns out that the true molecule is represented equally by the neutral and the formally charged zwitterion, where these are co-equal resonance structures. And what we can see now is that there's double bond character, where you have C partial double bond N. Which means that CN bond is especially strong and stable. And thus it's much stronger than a single bond. So in the left structure, the nitrogen appears to have 4 electron domains, and it appears to be sp3. But if it were sp3, then the lone pair would not be able to reside in a p orbital, because sp3 atoms hybridize all of their p orbitals. But now, in the zwitterionic resonance form, the nitrogen appears to be sp2. And that is the true story. It is actually sp2 always. It is never sp3. These are not 2 different molecules that are interconverting back and forth. They are always one hybrid molecule, which is a more complex, simply a more complex molecule that's partially described by each structure. We'll draw that hybrid on the next page. So to understand the hybridization of the nitrogen, you have to know something about pi delocalization. So the 6 coplanar atoms in the peptide plane, okay, these are going to be coplanar with trigonoplanar sp2 centers. And the sp2 carbons and other atoms are the nitrogen. We've just identified that as sp2, as it has a p orbital to develop a pi bond. This carbon here is sp2, it's also making a pi bond, and the oxygen made a pi bond in the other resonance form. So those are your sp2 hybridized atoms. I'll highlight them here as well. And anything that is attached directly to an sp2 atom is coplanar with that atom. So the coplanar atoms are the 3 in the amide functional group, and then the first sp3 carbon that is directly attached, along with the first sp3 carbon here that is directly attached, and of course the hydrogen. So that is your peptide plane. Every peptide bond has 6 coplanar atoms, which means that 2 consecutive alpha carbons lie in the same plane, always. Those alpha carbons are here and here. Beyond that, okay, you can't say that alpha carbons 1 and 3 are in the same plane, but you can say that 2 and 3 are, and 1 and 2 are. Okay, so any 2 consecutive alpha carbons are coplanar because of this zwitterionic resonance form. Because the peptide bond has double bond character, okay, we know that it cannot rotate. In other words, the peptide bond is rigid, as an alkene CC double bond would be. And that's going to cause the rotation to be limited to bonds that are simply single bonds. So for a peptide, we assign angles phi and psi, and let me do it on the other structure, which is cleaner. So we assign various phi and psi angles to describe rotation about the peptide plane, or the dihedral angles. And phi is the nitrogen to alpha carbon single bond. Phi describes the angles that you can have in various conformations by rotation around that bond. And psi describes the alpha carbon to carbonyl carbon bond. And it's allowed dihedral angles. So those do exhibit free rotation. But of course, there is going to be a limited number of stable conformations due to things like sterics. So I'll write that explicitly below, where phi is the nitrogen alpha carbon single bond and its favorable angles, while the carbonyl carbon to alpha carbon is described by psi. So because the peptide bond is rigid and cannot rotate, there are cis and trans configurations that cannot equilibrate because it would require the double bond to be broken for rotation to occur. So I'm simply going to draw two different conformations here. And we're going to focus on the bond that cannot rotate, the rigid amide bond. So in one case, I'm going to draw the nitrogen down to the hydrogen on one side, and I'm going to flip the other alpha carbon over to place R2 down as a dash. Okay, that's the L configuration. And if you were to simply take this and think about rotating that bond 180 degrees, then it would go to another conformation. And let me just show here that we have double bond character. That's why we cannot rotate this freely at room temperature. So what we have here are two different conformations. One where these R groups are cis to one another with a dihedral angle of 0. And then the other one, we've now rotated 180, where they're trans. In other words, you have to cross the peptide bond to go from one alpha carbon to the next. So those have a 180-degree dihedral angle. And almost every single amino acid prefers to form a peptide bond in the trans configuration. So if these were allowed to equilibrate upon addition of high temperature or UV light, and the bond were to break and rotate and then reform, you would find an equilibrium favoring more than 99% of trans and less than 1% of cis. For most amino acids, there's one exception, slight exception to that rule that we'll talk about in a minute. So there are multiple consequences of the zwitterionic resonance structure. Let me draw once again this delocalized electron entity. Because the oxygen takes on a formal negative charge in the zwitterionic form, that means that it is electron-rich, or that's the basic end of the amide. And thus it is an excellent hydrogen bond acceptor and is willing to reach out and interact non-covalently with other electron-poor protons. Because the nitrogen takes on a formal positive charge in the zwitterionic resonant form, it's going to appear partially positive in the true structure. But remember that nitrogen is much more electronegative than hydrogen. So the true positive charge actually lies on the hydrogen atom, which is being stolen from in an inductive or sigma sense by that highly electronegative sp2 nitrogen. So you can view this as being the electron-poor end of the amide bond, where it will be reasonably acidic with a pKa around 16. So that doesn't ionize under physiological conditions of pH 7, but it is going to be an excellent hydrogen bond donor. So every single peptide bond, I guess with the exception of proline, as we'll discuss later, is going to have this hydrogen bonding capability where you can make two of these interact with one another, where the amide oxygen of one can interact via a hydrogen bond with the amide proton of another. So that is your hydrogen bonding. It is non-covalent, but it is especially important when you have a large collection of hydrogen bonds. And amide functional groups are some of the best at hydrogen bonding. So these are excellent at hydrogen bonding because they have an electron-rich carbonyl oxygen and electron-poor amide proton. And it's all about charge here because hydrogen bonding is simply electrostatic. So in order to have this zwitterionic resonance form as an important resonance structure, we must ensure that the nitrogen of the amide, along with the carbonyl, carbon, along with the oxygen, they all must be coplanar, as we mentioned above. And the reason they must be coplanar is so that p orbitals can be parallel, where the nitrogen has a p orbital, where we show that as a lone pair, and it can interact with the simultaneously parallel p orbitals of C and O. And this is a 4 pi electron system, or they are conjugated in that you have continuous parallel p orbitals. And so this delocalization is explained by the resonance forms we drew above, but those 4 electrons are spread out throughout the 3 atoms and their 3 p orbitals. And it is incredibly difficult and requires a great input of energy to break that amide bond. That is why proteins are resistant to things like hydrolysis, etc. It's a very stable CN bond. And it's going to be resistant to change even upon heating or upon pH change. So I'll say it's resistant to delta pH or delta T. The only case in which that would break is if you do hydrolysis with a ton of water, strong acid, and lots of heat. So denaturing a protein will not affect this primary sequence. Peptide bonds are stable. Now, in order for those to be parallel p orbitals that are conjugated, they can only be in cis or trans conformation. So I've shown here that you have alpha carbons across or trans to one another, and it could rotate 180 to become cis, but it will not sit in any conformation or configuration in between those because the p orbitals must remain parallel. So they can either be straight up together like this, or one of them can rotate 180 for them to be parallel again. But you only see these limiting cis or trans. There's no other possible isomeric forms because those would not allow for conjugation. Now, I mentioned the trans, the cis ratio is normally greater than 99 to 1, but there's a proline exception. So for proline, it actually has a very sterically congested side chain. So let me draw a generic dipeptide where we have some R1, and then the cyclic secondary amine of proline has now formed a tertiary amide. And you could have the carbonyls in either cis or trans conformation. So this is the cis conformation, and it could also rotate if you broke amide bond and then it were allowed to reform. It could rotate over 180 to become trans. And let me just emphasize that, right? The bond that we're considering as a double bond or having double bond character is the amide bond, which lacks free rotation, and the alpha carbons are here and here. So there they are cis to one another or on the same side. If you cut down that peptide bond, and now you must cross this peptide bond to go from one alpha carbon to the next. And neither of these is great for proline. But proline, unlike the others, exhibits a little bit more of the cis configuration relative to trans. Trans is still favored, but it's not favored to a great extent because here you have steric clash between the carbonyl and the R group of amino acid 1. That's destabilizing cis to a great extent. But in the trans conformation, you still have steric clash between that R group of proline and R1. Right? Remember, there are, of course, hydrogens here that are branching out, and those would cause some steric strain. So the final consequence of the zwitterionic resonance form is the peptide plane, as I mentioned above. So you always have 6 coplanar atoms for every peptide bond. And as we mentioned before, that always places 2 consecutive alpha carbons coplanar. And we use phi and psi to describe the favorable dihedral angles between peptide planes. And I'll just emphasize again, those 6 coplanar atoms are these. C alpha 2, C alpha 1, and then the amide functionality. Okay. So that's all I have to say about primary sequence and peptide bonds. And to learn more, you should visit my course guide at chemguides.com and do relevant problems in Unit 1 that discuss peptide bond, zwitterionic resonance structures, hydrolysis, condensation, and primary structure, etc.